Okay, this is going to be our fourth and final video in this module. And again, this module corresponds to Chapter 5 in the textbook. And everything we're talking about here is going to correspond to Section 5.3 in the textbook. They go into some more detail that we're really not going to need for this course, so I'm just going to cover the main parts, and really you need to focus on sort of Hooke's law, where it's applicable, and how to use it, which is what we're going to talk about here. Okay, so we can get into it now. We start off talking about elasticity, stress, and strain, right? So what's really going on here? Well, what we're talking about here is that bodies deform if a force is applied to them. So this is clear in some cases. If you have a block of rubber, let's say, and you apply a force to it, you can really see this very clearly. But this is true for all materials. So whether we're dealing with a spring or a block of rubber or a block of wood or a block of glass or ice or whatever, it doesn't really matter. All these materials are gonna deform and then fracture in similar ways. Now, when I say similar, I don't mean that we need the same amount of pressure, or even that the ratios at which these things are going to happen are going to be the same. But we're going to see from the plot later on that there are some similarities. Okay, and so a pattern that they're all going to follow is, at first they're all going to deform elastically. So when I say deform elastically, this means deform in such a way that they're going to return to their original shape when the applied force is removed. Then after we apply too much force, if we keep cranking the force up, they're going to deform in such a way that they're going to deform permanently. And this means that they're going to deform in such a way that that they're not going to return to their original shape. And finally, if we apply sufficient force, they're all going to fracture, right? If we apply enough force, eventually whatever this object is going to fracture. Okay, and so all these objects will have a deformation or a delta x versus applied force plot that are going to follow the same sort of general shape. And I'm going to draw this plot down here in the space that we have in a second. But let's remember that they're all going to that all materials, all objects are going to follow this general shape, even if the scale may vary and the relative size of the regions may vary. And I'll talk more about that here as I draw it out. So bear with me while I draw this. So imagine that we have a plot here. And maybe it would have been good to leave a little more space on the bottom here, so let's do it like this. Okay, so on this axis, let's call this force. Okay, so this is the force that we're applying to the object. And on this axis, we're going to have our deformation. I'm just going to call this x. This could also be delta x, right? And so what is this going to look like? I'll just draw the shape here, and then we'll talk about the regions. First, we're going to have some linear region. Then we're going to have, maybe I'll do that. Then we're going to have some curved region that looks something like this. And this plot is also in your text, so if you want a more nicely drawn version of it, you can just look it up in the text. But I'll draw it here just so we can discuss some of the features of it. That should maybe be smoother than I drew it, but it'll do for now. Okay, so what do we have here? We can imagine that what's happening. We have our object, whatever, some cube of something, right? We're applying force to it, and as we apply more and more force, we're applying more and more force. This thing starts to first deform in such a way that when we remove the force, it'll pop back to its shape. Then it starts to deform such that even if we remove the force, it'll be permanently deformed. And finally, if we apply enough force, this thing is going to shatter, right, or break. And so this first region here, actually these first two regions, we group up, and this is what we call our elastic region. So in this region, first we have this linear region here, and then we have this nonlinear region over here. But in both of these regions, this is where the object is deforming and then returning to its original shape, right? And then over here we have our permanent deformation region. Oops. It's going to be hard to read, but you get the idea. And then finally, this line here, that's our fracture. Okay. So if we apply enough force that we're beyond that line, this thing has fractured, and obviously it's not going back to its original shape. Okay, so this nonlinear region also extends, and maybe I'll just extend this out instead of drawing another one. This is all nonlinear here. Okay. So as I mentioned before, regardless of whether we're dealing with a block of rubber or a block of glass, this is going to happen for all these objects, except that in the case of a block of glass, it may happen that all these first three regions are extremely small, right? They're all bunched up in the beginning, and either we're applying force and then very quickly we go through all three regions, and either it does nothing or fractures, kind of thing, right? Or for example, for a block of clay, which very quickly will progress to the point where you're getting permanent deformation. This region may be very, very small, and then we're into the permanent deformation region that may be very, very large, and then only very, very close to the end do we get the fracture region once we've applied enough force to actually sever this thing, right? So you can imagine that for different materials, there's going to be different ratios, right? Like these regions won't always be in the same size related to one another, and the amount of force needed to be applied to get these different amounts of elastic or permanent deformation will vary, but they all have this basic shape, be it either bunched up or not, right? In any case, we're going to be particularly interested in this linear region in here. Okay, this linear region where we have this elastic deformation and the deformation is linear, and by linear I mean that this is a straight line. This line in here is supposed to be a straight line. In this region, this is the region in which Hooke's law is obeyed. Okay, so in that region we have Hooke's law, and that's what we're going to want to take a look at now. Okay, let me scroll down a little bit here. So in this first region, this linear elastic deformation region is where Hooke's law is obeyed, and Hooke's law is given by this equation here. So I've written it in two different ways. I've written it where we have delta x, where the deformation is represented as a change in x. But if we set our initial x to 0, then really it just becomes this equation here. And this is the way I'm usually going to write it. Okay. And so our x, or our delta x, is a measure of the deformation as it was in this plot here. It's our vertical axis here. And this k is just a proportionality constant that is going to be unique to whatever item or object we're deforming, right? So if you're dealing with a block of glass or something, it's going to have 1k, or if you're dealing, well, I mean, its k is going to be extremely, it's not going to have a very large region of applicability, because for a block of glass, you get through the elastic and permanent deformation regions extremely quickly, and you're going to have this thing shatter almost right away as you apply enough force to it. But let's say you're dealing with whatever. We're usually going to use this for springs. So in the case of springs, we're going to have a proportionality constant that's sometimes called a spring constant if we're dealing with springs, and it's going to have SI units of kilograms per second squared. Okay, so for whatever spring you're dealing with, and again, this is where we're usually going to be applying this in the case of springs, you're going to have some spring constant, and you'll either have to calculate the spring constant or it'll be given to you and you'll work with it, right? And we're going to take a look at an example of that right now. So So let's say we have a spring, which we know obeys Hooke's law. So we're only applying enough force that that the spring remains in the region of applicability of Hooke's law. So it's only in the linear region where we have elastic deformation. And so we have this spring, and in this example, our spring has the spring constant of 50 kilograms per second squared. And the spring is hung from the ceiling from a hook, and at the bottom of the hook we hang a 1 kilogram mass, right? And we want to find what the deformation of the spring is. So let's just quickly draw this out. Let's say we have the ceiling here, we have some sort of a hook or something. We hang our spring, and we hang a mass here where the mass is equal to 1 kilogram. Right? So before we had anything, so let's say this is like a before and after. So let's say we had this before. So let's say we had this, yeah, something like this. Right, so before we had the spring, it wasn't stretched out, it was just hanging from the ceiling. We hang the mass on it, and now the spring sags down a little bit. And what we want is we want to find this, what I'm going to call x, or you could also call delta x, but I'm going to call it x. We're going to set this upper line here to x equals 0, and so this bottom line will be x equals xf, which will just be what we call x, right? And so we want to find what that x is. Okay, so from here, and maybe I've drawn this way smaller than I needed to, but whatever. From here, we're going to jump right back into the free body diagram. Okay, so free body diagram, useful in many cases, as it is here. And so what do we have? Well, so on that bottom piece of spring, what's happening? Well, we have the force of gravity pulling down because we have that mass hanging from it. That's just going to be mg. And pulling upward, we're going to have the force of our spring, which I'm just going to call F here, right? And if we use Newton's second law again, maybe I'll make a note of that. So N2 implies that F net, and we've ended up calling this the x direction because of the way I've labeled that x. So that's fine. It doesn't really matter. We could have called it y. It doesn't matter what we call it, right? So F net. And I won't put the y or x subscript here. F net is going to be equal to the mass times the acceleration. Again, once this mass has extended the spring, there's no longer any acceleration. We're in a stable state here, so our acceleration is going to be 0. So this is going to be equal to 0. But our net force is also equal to F in the positive direction and mg in the negative direction. Because these are equal to 0, again, this means that F is equal to mg. But we also know from Hooke's law, and we're told that we're in the region of applicability of Hooke's law for this spring. We know that F is also equal to kx, right, from our expression above. So we can replace the F on the left with kx, and we end up with this equation here. And at this point, it's just a matter of rearranging. We just want to find what x is. We want to know what that deformation of the spring is. And so we're just going to isolate x. So we have mg over k. And now all we need to do is make the replacements, right? So we just substitute in what we know. We know that mass is 1. It's 1 kilogram, 9.8 meters per second squared is our gravitational acceleration, and our spring constant is 50 kilograms per second squared. If we do all that, we could double check the units, and if we did all that, we would find that we have a deformation of x equals 0.20 meters. Okay, and that would be the answer to this one. And so we're gonna run into springs again in the future, but this kind of gives us a flavor of what it is, what force this spring is applying and why. And it's because the spring obeys the spring in this region obeys Hooke's law, and Hooke's law gives us the force that that the spring is exerting.